All right, guys, so let's take a look at ion concentrations for acids and bases. And if we look at Model 2, we've got a whole series of solution. On the top, they're acidic, they move to neutral, and the bottom groups we have are basic. But take a look at the concentrations of at the H plus. So remember when it's in solution, that H plus likes to grab onto a water molecule, making this H3O plus, or a hydronium ion. Let's go ahead and write that. So that's known as our hydronium ion. Okay, so H3O plus. Oh, ran out of space. Sorry about that. Okay. And then over here, we have also our OH minus concentration. And there's an interesting thing, and I really would like you to pause the video, but if you take a look at all of those, every single one, doesn't matter. If we take the hydronium ion concentration and we multiply that by the hydroxide ion concentration, every single one of these will end up giving us 1.0 times 10 to the negative 14. Okay, and that's really significant for us because that relationship always holds, we can use that to do some pretty interesting things. So this value, this 1.0 times 10 to the negative 14th, that is also known as, looking right down here, the auto-ionization of water constant, right, Kw. And Kw comes from this equilibrium that we have right here, all right, where we have a water molecule and another water molecule, and one of those water molecules takes hydrogen from the other water molecule, giving us an H3O plus and an OH minus. So what that means, which you should have seen also from the last video or last section, water, right, is amphoteric. Amphoteric, meaning it can be an acid or a base. So right here, this guy here, he's acting like a base because he's grabbing a proton off of the other water. And then this guy here, he's acting like an acid because he's donating that proton. All right. But what's interesting is whether it is water that is ionizing or if we've got an acid or a base in the water, those concentrations of H3O plus times OH minus will forever and for always be 1.0 times 10 to the negative 14th. Then another interesting thing, all right, so this always holds true. If it's a water solution, that is going to hold true. And then if we take a minute and we remember back to math class, if you have a number like 1 times 10 to the negative 14 or 1 times 10 to the negative 4, and if you take the log of it, you notice that, or you should notice, that whatever the exponent is on that 10 comes down and becomes our answer. So you can do this without a calculator if it is in the form of you're taking a log of any number that's 1 times 10 to, let's say, negative 5th, then that would be equal to negative 5. Okay, if it's in that form, you can do it without a calculator. We just take that number down. And if it's not, you would actually need to use a calculator to get the value. Now that's important for us here in the next slide. So notice on this Model 3, when we write those concentrations of H3O plus in our scientific notation, especially if we look at solutions A and C, those are written real nicely for us. Notice that if the concentration of H3O plus was 1.0 times 10 to the negative third, notice when we take the log of that, our answer is negative 3, and the pH we write as 3. So from that, we should be able to notice that the formula to calculate the pH of a solution is going to be the opposite or negative of whatever the log of that concentration oops, that's a 3, is. Okay, so if I take the log, I end up with -3, but my pH I report as 3, so pH is going to be negative log of the concentration of H3O+. And if we look here at model 4, notice that if we have a solution, right, we noticed from the last slide, concentration of OH times concentration of H3O+ will always and forever equal 1 times 10 to the negative 14. So if we know one, we can figure out the other. But notice here, there's kind of something interesting. So if I take the pH, all right, so if I take the pH of, let's look at A. So I take that pH, so that negative log of 1 times 10 to the negative 3rd, that is equal to a pH of 3, we notice here. And notice I can do the same thing here for OH, and instead of calling it pH, I'm going to call it POH because it's the power of the hydronium ion or power of the hydroxide ion. And so I would take the negative log of 1 times 10 to the negative 11, and that equals 11. And notice, if I add my pH plus my POH of any solution, what value do you notice that it becomes? Well, 3 plus 11 is 14. And this is a hugely useful relationship to remember. Okay, so knowing that to get pH, you're going to take a negative log of a concentration. And if I know pH, and if I remember this relationship, if I know pH, I could figure out POH and vice versa because they always add up to 14.